during the presentation?
Yes, the camera is off, or is on.
On radio.
Yes, absolutely. Okay. Would you want to begin?
Sure. Hello everyone, my name is Xu Mao. Today I'm here to present my research. The title of my research is Backlash Reduction in Parallel Manipulator using Actuation Redundancy. My former supervisor, Dr. Ron Potorodowski. My current supervisor is Dr. Yang Xin. The presentation is divided into introduction, objective, challenge of my research, state of art currently, and the work have been accomplished, and later I will give the conclusions. Here are some example applications of parallel and serial robots. The figure on the left-hand side, it is robotics arm carry out the movements to perform the actual surgery on a patient. So the robotics is used to allow the surgeon to be distal to the patient. The figure on the right-hand side, it is Dexter robots. It's designed for space, station, maintenance, and service. Compared to serial robots, the parallel robots can provide higher rigidity and could provide higher accuracy, be more compact in structure, have more payload capacity because of the multiple branches. The one on the left-hand side, it is stored Golf spatial parallel manipulator, and it is used for flight simulation. The one on the right-hand side, it is planar 3RR parallel manipulator with the first bench actuated. The disadvantage of parallel robots include because they use the actuated joint that have backlash problem, and because of the multiple branches, so it limits the working area. The figure on the left-hand side, it is a circular path generated by a parallel manipulator and effector. It doesn't have any backlash problem, so you can see the circular path is smooth and nice. The other figure is because of the backlash problem, so you can see the trajectory is kind of jagged. One way to improve the precision, get rid of the backlash, is use the Bosco slide. So here I have the images showing how does the Bosco slide look like, but using the Bosco slide increase the cost tremendously. In order to get rid of the backlash, monolithic flex joint have been proposed to replace the traditional mechanical joints. And because of the monolithic joint have a really limited range of motion, so it really limits to the applications. Here is the area of my study, is to reduce the backlash problem in parallel manipulator, and it could to achieve getting better accuracy in the parallel manipulator. Backlash reduction in planar parallel manipulator through the use actuation redundancy will be considered for the RRR parallel manipulator and for the RPR parallel manipulator. The important method I'm using for my research is adding actuation redundancy in branch. School coordinates matrix of the associated reciprocal school are used to model the force capability and the motion capability of parallel manipulator. No space-based vector of the ARS matrix and their multipliers are used to allow the backlash reduction through the elbow joint torques based compensation. And nonlinear constraint optimization technique are used to ensure no reversing sign of the actuator output torques or force for the prismatic joint. Here is the state of art. In 1987, Gosselin and Angelis, they were the first to propose the non-redundant layout of 3RR parallel manipulator. So they actuated the base joint, but they cannot control the backlash by active control of actuated joints. Ken, in 2005, he used the flexure joint to replace the traditional mechanical joint. But like we said before, the flexure joint have a really limited range of motion to the applications. In 2005, Mueller, and 2007, Mueller and Maser measured together. They considered to adding additional branch. So they have 4 RRR parallel manipulator. They could control the joint torques of the redundant branch, but the extra branch limit the working area of the workspace. In 2010, we and Simon, they used a preloading spring at the wrist joint of planar 3 PRR parallel manipulator to eliminate the backlash problem in the prismatic joint. This is really good this is really good way because the cost is really not expensive and they can address the problem. But they cannot control how much torques have to be applied, and they only can eliminate the backlash for a certain range of the applied force and the moment. So here is the layout of the parallel manipulator using for my research. The RRR parallel manipulator on the left-hand side and the RPR system on the right-hand side. If we actuated the base joint of the RRR parallel manipulator, B1, we can find the associated reciprocal spool. It will be associated with this revolute joint, and it will reciprocal to the other two joints in the same branch, E1 and the W1. So it will intersect with E1 and W1, point right there, $'11. For the RPR PM, if we actuated the revolute joint of first branch, B1, we can find the associated reciprocal spool. It will associate with E1, and it will intersect with the wrist joint, W1. It will be perpendicular to the prismatic joint. It's point right there, $'11. The associated reciprocal spool, it is used to allow to model the force capability and the motion capability. So it will allow to find the required torques of force for the actuated joints. Now let's consider the working area. So the circle construction utilized to determine the working area. The working area for the RRR parallel manipulator is due to the branch. Each branch have a 0.3 meter, so it allowed each branch have a vary from 0 to 0.6 meter. So the working area is determined by the three large radius of the circle in the center, highlighted by the shading. They have a separate picture showing in the center. For the RPR parallel manipulator, because the prismatic joint have a limit lower length is 0.3 meter, so the value of the branch is from 0.3 to 0.6. It will narrow down the working area for the RPR parallel manipulator, and the figure showing on the right-hand side. To accommodate the trajectories, so the prismatic joint have been modified. We consider they have a relative length. The relative length will all relative to the joint, revolute joint R1I. So the relative will have a capable length issue from 0 to 0.6, and it will allow the prismatic joint have a 0 to 0.6 meter, and they could give us the consist working area like RR system. The chosen trajectory are circle trajectory, spiral trajectory, and the large radius of arc trajectory. They are all reachable area inside of the working area for the both RR and RPR. And during the generate the trajectory, we suppose they always have 100 Newton afford for the acting on the manipulator, and it's always tangent to the trajectory and opposite to the motion. So now let's consider the non-redundant actuation. So if we actuated the three base joint for both RR and RPR parallel manipulator, so we can use the function showing on the top. It is a force summation. It is in terms of wrench intensity of actuated joint torques, and in terms of ARS of actuated joints. We could rewrite this equation by using matrix algebra. We can firm the redundance space. We can firm the ARSs into a 3x3 matrix and collect the wrench intensity into 3x1 vector. So from the equation next, F equal to $'3 multiplied by W3, we can find the wrench intensity of each actuated base joint or elbow joint. The torques, we can find the required torques using next equation. Torques equal to wrench intensity multiplied by the associated reciprocal spool reciprocal product with the original spool coordinates. It is related to the mechanical advantage of actuated joint. The circle star is a reciprocal product. So here is the performance evaluation for non-redundant actuation. On the left-hand side, it is actuated the base joint on the top, elbow joint on the bottom, and on the right-hand side, it is RPR parallel manipulator for actuated the base joint and the prismatic joint. We can see the curves, they are crossing line 0. Once they crossing line 0, that's the moment to allow the backlash occur. So the backlash problem is for each of actuated joint. They have a backlash problem. Now let's consider the redundant actuation. So if we actuated the base joint and the elbow joint for both RRR and RPR for each of the branch, we can find the 6 different associated reciprocal school. It could form the 3x6 matrix $'6. 3 is corresponding to the 3-dimension force capability, F in x direction, F in y direction, and the moment along the jet direction. And for the force, for the range intensity, is a 6x1 vector. By solving this equation, we use a Redmond-Penrose pseudo-inverse of the matrix. Here is the definition for the Redmond-Penrose pseudo-inverse, and we can find the range intensity using the torques equation that will help us to find the required torques or force for the actuated joints. It will give us the minimum true norm solution. So here is the evaluation for the pseudo-inverse solution for the RRR and RPR. Follow the circle trajectory, and we can see it does reduce the amplitude for each of the actuated joints, but they are still crossing line 0, so for each of the actuated joint, they still have a backlash problem. To continue with the general solution, we solve it using a no-space space vector of the matrix. By using no-space space vector of the matrix, multiply its parameter could help to find a single sense solution of the range intensity. So we suppose here is how do we find the no-space space vector, and continue with the general range intensity. It is in terms of a particular range intensity plus the homogeneous range intensity. The particular range intensity, we could, in my case, I chose the non-redundant case as a particular range intensity. The homogeneous solution, it is in terms of no space vectors solution multiplied by the elbow joint range intensity. So by solving this equation, we can find the general range intensity for the manipulator. Let's think about optimization. I choose the objective function showing on the top, minimize this objective function along the trajectory divided into 200 intervals to achieve 201 points. In each point, each moment, we will have 6 different torques or force applied for the system. So the cost function is L equal to the torques function, and the torques is represented for the 6 different actuated joint and along the trajectory for different moment. We designed the base joint range intensity. So the sine wave equation are used to design the range intensity of the base joint. In this equation, it is sine wave equation. I have a Wi, it is a mean value. Alpha I, it is a factor setting the amplitude. Gamma I, it is phase angle. So if we set the alpha I is always greater than 0, smaller than 1, it will guarantee that desired range intensity never cross line 0. It will always stay in the positive or negative for the base joint. And during the optimization, we added a no reversing sign of computed elbow torques in the optimization routine to ensure the no reversing sign for the elbow compensation the torques. We did for the optimization for each cases for the RR and RPR. 8 different combinations of sign are possible for the desired range intensity of the base joint. So the base joint torques could always be positive and negative. And the constrained optimization is used to find an optimal single sense solution to the elbow joint torques. Here is the table for one of the case for the RRR, follow the circle trajectory, and the 8 different combinations are tasked to find the best result. Some of them, they have a better performance than the others. Some of them even didn't converge. So the last row is involved with the average absolute value along the trajectory. And we can see the evaluation for this case. And none of them are crossing line 0, so we have a backlash free for this case. And next we test for the spiral trajectory. We find the optimal solution, and they have a 0 backlash. And the arc trajectory for the RPRR parallel manipulator. Continue with the test. We find because the prismatic joint, if we actuate it, they have to apply the force due to this. So meeting factor are utilized to make the torques and the force have a consist value in the objective function. And we did 8 different combination tests for the base joint torques and follow the circle trajectory. Here have the performance evaluation for the circle trajectory for the RPR system. Desired range intensity on the left-hand side and the force for the prismatic joint as a compensation. So they have a 0 backlash. Here is the conclusion of my research. We proved the invariance of a reciprocal product to changes in reference frame, location, and orientation. P-joint, prismatic joint have been modified to allow the 0 relative displacement. And the 3 RPR, force uncertainty configuration have been demonstrated due to the platform and the base edge alignment. No reversing function to ensure no reversing sign. First joint range intensity and constraint to ensure the no reversing second joint value have been presented in my dissertation. The advantage of the method of the algorithm is we use the optimization-based solution could reduce the torques of the base joint. Backlash reduction through the joint actuated redundancy is possible. Here is the shortcomings. It's only true for the certain range of the force and the torques and the higher cost required compared to V and Siemens spring, passive spring for the PRR system. And here is the publications, and I'm still working on the last paper now. Hope I can get it submit soon. Thank you so much.
Thank you. Okay, so we'll begin with questions. Can you move to external examiner?
Okay. Thank you. I just want to mention that I enjoyed